So far, in our reactor design equations, we've been considering only simple reactions that are elementary as written. What this means is if we have a reaction A plus B going to C, we can write that the rate of consumption of A is simply equal to a reaction rate constant times the concentration of A times the concentration of B. While this may be a useful approximation, elementary reactions are quite uncommon. Typically, the stoichiometric equation actually represents the summary of a much more complicated series of bond breaking and bond making steps. For instance, for the reaction N2 plus O2, reversibly giving us 2 molecules of NO, the reaction in one step, so we could draw this essentially like this, where we have some complex being formed between diatomic nitrogen and diatomic oxygen, going in one step to making 2 NO molecules, is extremely improbable. In reality, the reaction probably proceeds through a sequence of elementary steps. So it might look something like this, where N2 first reacts with an oxygen atom to form NO plus a nitrogen atom, and then that nitrogen atom reacts with diatomic oxygen to form another NO plus O. So altogether, this sequence of steps gives us the overall stoichiometry of the reaction, N2 plus O2 giving us 2 NO molecules. So how do we describe the rates of these more complicated reactions given information about the sequence of elementary steps or reaction mechanism by which they occur? So that'll be the question that we'll be trying to answer over the next few lectures. So to summarize this, we want, starting from a sequence of elementary steps or reaction mechanism, we want to get a rate expression that describes the rate of formation of species as a function of concentrations or partial pressures on temperature. Let's consider this for an example reaction, the decomposition of ozone, which is O3, in the presence of oxygen atoms. So the reaction stoichiometry here is O3 reacting with an oxygen atom to form 2 molecules of diatomic oxygen. In the next video, we'll develop a rate expression for this reaction. But first, we'll see that it provides a nice example to develop a useful approximation in solving these types of problems. It's observed that the reaction proceeds much more rapidly in the presence of chlorine atoms, but that they're not consumed as a stoichiometric reactant in the reaction. So the sequence of elementary steps for the chlorine catalyzed route might be a chlorine atom reacting with O3 to produce O2 and ClO. That ClO can then react in a second step with an oxygen atom to form another O2 molecule and to regenerate that chlorine. So overall, the reaction stoichiometry is O3 plus O going to 2 molecules of O2. Now this sequence of steps looks similar to the series reaction that we analyzed previously. So this looks a lot like A going to B with some reaction rate constant K1, and then B going to C with another reaction rate constant K2. So we solved this problem previously, writing mole balances on each species. So for example, in a constant volume batch stirred tank reactor, we could write that dCA dt was equal to minus K1Ca, dCB dt was equal to the rate of the first reaction, which produced B, minus the rate of the second reaction, which consumed B. And finally, you could write dCC dt was simply equal to K2Cb. So we solved for the concentration of A as a function of time by separating and integrating the mole balance on A. inserting this expression in the mole balance on B yielded a linear first order differential equation, which we solved using an integrating factor. The concentration versus time profiles looked something like this. So I'll plot it first. So if I look at the normalized concentration of each species versus time, A monotonically decayed, B initially increased, went through a maximum, and then decreased as eventually it was converted to C in the reactor. So we developed analytical expressions for the time at which B is maximized here. And so that was dependent on our two reaction rate constants, K2 and K1. And we solved for the concentration at that point, Cb max. That was equal to Ca naught times the ratio of K1 to K2 raised to this power, so K2 over K2 minus K1. Now let's suppose that B is a very reactive intermediate, which means that K2 is much, much greater than K1. So suppose K2 is much, much greater than K1. So this would simplify our concentration profile for B from something that looks like this. So Cb being equal to Ca naught times K1 over K2 minus K1 times e to the minus K1t minus e to the minus K2t. So here, if K2 is much, much greater than K1, we can approximate Cb as Ca naught times the ratio of K1 over K2 times e to the minus K1t. So if we remember that Ca in this problem was equal to Ca naught times e to the minus K1t, and Cb is simply equal to K1 over K2 times Ca, then we can write that K2 times Cb minus K1 times Ca is equal to 0. So if we multiply this expression by minus 1, we can see it's identical to our mole balance on B. So this left-hand side is simply our mole balance on B, dCb dt. So what this means is that under these conditions, dCb dt is approximately equal to 0. So this approximation, that if B is a very reactive intermediate, the derivative of the concentration of B with respect to time is approximately equal to 0. We call this the pseudo-steady state approximation. So this simplifies the development of our rate expressions significantly. But how can we make sense of this physically? So from our previous expression, we can see that if the second reaction rate constant, K2, so if we look at these two expressions, if K2 is much, much greater than K1, the time at which the concentration of B will go through a maximum will tend towards 0. Additionally, the concentration at that maximum, so Cb max, is also going to go towards 0. This means that the steady state concentrations of reactive intermediates are small compared to the stable reactants and products, so in this case A and C, and the time to reach this situation is small relative to the reaction time. Another consequence of this is that if from the mole balances we can see that essentially if we just added all the mole balances together, so dCa dt plus dCb dt plus dCc dt equals 0, if the pseudo-steady state approximation is applicable, so if PSSA applies, then we can write that dCA dt is approximately equal to minus dCC dt. So note here that a more precise definition of the pseudo-steady state approximation is that the magnitude of dCB dt is simply much less than that of dCA dt or dCC dt. So rather than it being precisely equal to 0, it's rather that this derivative with respect to time is much smaller than those of reactants and products. So when can we apply this approximation? So for homogeneous systems, so reactions in a gas phase, we need some information about the reactivity of our intermediates. So we need to know that our intermediate species is very reactive, and therefore the rate of the reaction that consumes it is very rapid. For solid catalyzed heterogeneous reactions, which we'll spend some time thinking about soon, since the number of reactive intermediates is bound by the number of sites on the catalyst, it turns out that the pseudo-steady state approximation is always valid. All that is required is that the number of reactant molecules turned over needs to be much greater than the number of active sites. So for any reaction we consider to be truly catalytic, each site turns over many times. So in the next few videos, we'll see the utility of the pseudo-steady state approximation in allowing us to develop rate expressions given a sequence of elementary steps.